All right, well, good afternoon, everybody. Thanks for coming. Welcome to the latest Iris Early Career Flavored webinar. This is your host, Andy Frisetto, aka the Iris Swiss Army Knife, speaking to you from the headquarters of the Incorporated Research Institutions for Seismology in Washington, D.C. If you're familiar with IRIS, you know it's a nearly 30-year-old consortium of universities interested in seismology and also an NSF funded seismology scientific facility that operates programs enabling earth science to do a broad spectrum of research in geophysics, particularly in seismology. So, the motivation for today's webinar is part of a series that highlights professional development topics aimed basically at lowering the energy and knowledge barriers associated with careers in science, particularly the academic track. So, if you're interested in additional resources in this vein, you would go to www.iris.edu/hq/ECI. That's our early careers page. And then the page where this webinar is going to be recorded and archived after today is the Iris YouTube channel. We're developing a new page that'll run off of the Iris website that sort of has information about all the webinars. But if you go directly to the source, that's where you can get this information currently. And so that's the Iris EPO channel or Iris ENO username on YouTube. If you scroll down to webinars and long Earth science lectures, you'll see that list of webinars. And if you scrolled over a little bit and then clicked on it, you would see that today's webinar is a bit of a sequel because Heather gave a webinar on Antelope and SAC about a year and a half ago. And so you can go and catch up on that if you haven't seen that one first. So, just some of the ground rules for how we do the webinars. Only Heather and I are going to be the only two people with voices. And while she's giving her presentation, I'll be muted. In the end, I will parrot any questions or comments that you have related to what was just presented. And so the way that we'll do that is just type your question or comment into the webinar control panel box that says questions, and those are going to register on my end, and then I will read those off. What I'll do is I'll read your name and the question. If as all these have been accumulated, there are questions that are duplicates, I'll probably just read the first one or try to combine them all into one mega question and then skip over ones that are redundant. If the webinar crashes, sit tight. It's capable of being rebooted, and so it usually takes just a couple minutes on my end, and then just click the same registration link you got when you signed up in the first place. And I always say this, I like to take an informal survey of groups that are watching out there. So if it's more than just you at your computer, if it's a lab group or something, let me know a head count. So beyond just the number that I see in my window for individuals who registered, it's always good to know the broader uh, audiences. So without further ado, I want to introduce our speaker. Our speaker today is Dr. Heather DeShon. She, as I mentioned, she's the first alumni of our webinar series to come back and give it a second go. Heather is currently an associate professor at Southern Methodist University in Dallas, Texas, which is in fact where she earned her bachelor's degree in geophysics and math before going on to get a PhD at the University of California, Santa Cruz, studying the Costa Rican subduction zone. So, Heather, I'll turn it over to you for your presentation, Antelope Strikes Back, using the Perl and Matlab interfaces to your advantage. And when I send the screen sharing over, Heather, it's going to hiccup your audio for a second, so just be aware of that.
Okay.
Okay, and there it should go.
All right. Can everyone hear me?
Yes.
Okay. Let's get this out of the way here. So I stole Andy's title, Antelope Strikes Back. This presentation today is going to be about the Perl and Matlab interfaces that come with Antelope. And I'll say at the onset that it's really geared to graduate students or those who haven't used the Perl and MATLAB interfaces before. So the examples I'll show should be pretty straightforward, but a little low level, and if you're interested in seeing the scripts or having a copy of anything I talk about today, you can just send me an email. So I want to talk about Perl and Antelope first, and I'm going to go over a basic Perl script that shows data reformatting, so text file to text file reformatting. Then I'll show how to extract and add information to an Antelope database within a Perl script, and then go over an example that I use when I integrate US array data with other networks. And then we'll switch over to MATLAB, hopefully about halfway through the talk. We'll review some of Kent Lindquist's tutorials that come with the MATLAB Antelope interface, and then I'll go over some examples coming out of array processing, noise analysis, and an example using Gizmo, Antelope, and MATLAB. And Gizmo is a waveform cross-correlation package. Just to make sure everyone's on the same page, I did want to spend a little bit of time reminding everyone what Antelope is. It's a software package that was designed to acquire, distribute, and archive environmental data and do some processing. It does handle real-time and offline batch mode data, so it can be used to run a network, or it can be used offline to look at data that was gathered, you know, a month ago or years ago. Today, we're really going to focus on the offline batch mode aspect of Antelope. It is the property of Boulder Real-Time Technologies, or BRTT, and the way it works is they distribute it to U.S. academic research institutions for use with Pascal deployments, US array, DMS archiving, and academic research. So there's an agreement that you can find on their website that outlines what you are and are not allowed to use Antelope for. Why do we use it? First, at its heart, it was originally designed to deal with seismic data, so it still deals with seismic data very well. It comes with a bunch of tools that will allow you to process and analyze seismic data, and what I like about it is that you can put different formats of seismic data into a single database, and it treats it all the same. So you don't have to worry so much about which waveforms are SAC or which waveforms are mini-seed, that sort of thing. It's flexible so that you can create your own tables and integrate your own location algorithms or magnitude calculators into it. And then, of course, since I'm at a US institution, it is free, but you can't beat free. I'm just going to go over some definitions. This was all covered more extensively in my original Antelope webinar, but Antelope at its heart is driven by a relational database, so we have to go over some relational database definitions. First, it works with tables. These are fixed format ASCII text files. They're made up of rows and columns. Now, in relational databases, the rows are called records and the columns are called fields. If you're coming from a GIS perspective, you might be used to thinking of the columns by the name attribute. All right? But the idea is that each record is a unique combination of information, and the fields have, in our jargon, certain attributes in every table that they appear in. All right? And then the whole thing gets put together using files called schema files, which define which tables and which fields make up records. Okay, so it's the broad scale definition of what makes a database. This example is the CSS 3.0. There is now CSS 3.1. This is from a few years ago, so this is CSS 3.0, the Center for Seismic Studies schema version 3.0, and this is a very common schema that gets used in passive source seismology. All right. Now the schema also defines what make up the primary and alternative keys of each table. This is an example of a site table from the CSS 3.0 database. And in the site table, the primary keys, the keys that have to exist in order for the table to be complete, are station, on date, and off date. Now another table is the site channel table, and for that table the primary key is channel ID, but there's these alternate keys, station, channel, on date, and off date, and the database is set up so that it knows how to link tables together by matching up either primary or alternate keys. Okay, so the fact that these two tables both have station, on date, and off date will let you link these tables together. All right, the last thing I want to make sure that we're all on the same page about is how Antelope handles time. It handles time as epoch seconds. So this is seconds since 12 a.m. on January 1st, 1970. It turns time into standardized floating point number. Okay, so an example would be down here at the bottom of the slide where you have this big number that's starting with 13. Okay, so that's what I mean, seconds since January 1st, 1970. By doing this, it really simplifies any calculations involving time, and then Antelope comes with a number of time-related tools, including the command line tool epoch, which allow you to switch from, we'll call the regular date time over here, readable time, to this epoch seconds time. All right, so before we get going, I also have some prompts that I want to go over. So anytime on my slides in this talk that you see the 2 greater than signs, that indicates that I'm writing in MATLAB. Okay, so that's the MATLAB command line. Anytime you see the percentage, it indicates that I'm on my Unix command line, like TC shell, so that's my TC shell command line. Now when we get into Perl, I'm really be writing into text files, so if there is no prompt out in front of something that looks like a command or something, then that indicates that I'm either writing a Perl script or a MATLAB function. All right, but either way, it's in a text file. Okay, let's start with Perl. Now, Perl stands for Practical Extraction and Report Language, or Pathologically Eclectic Rubbish Lister. So it was originally designed by Larry Wall, and the nice thing about Perl is that it really simplifies common tasks. Okay, so if you're writing something really easy, you might want to write it in a shell script. It gets a little more complicated, but not so complicated that you want to switch over to C or MATLAB, or since we're seismologists, Fortran, then Perl might be a good option to use. Now it's pretty quick and easy to write. You can manipulate data in a fairly complex fashion. It's particularly easy to learn if you're like me and learn C as your first language, programming language, of course. You create text files with sequences of commands that are then compiled when the script is invoked. So we'll look at an example. It looks like C. It contains a lot of the functionality of C, including strings, arrays, associative arrays, and pointers, but it doesn't require the explicit data type declarations or the standard libraries and that sort of thing like C. So you don't have to define everything in advance, and etc. It's portable, and it's usually comes with most of the machines that we all order now. All right. Why do I like it? What is its perceived usefulness for seismologists? From my perspective, I use it a lot for reformatting text files. I do a lot of earthquake location and waveform cross correlation. I use a lot of different codes. Everybody's codes have slightly different input file formats, and Perl is a really convenient way to write scripts that allow you to switch from one input format to another input format. Because it does have an interface with Antelope, it's really powerful for extracting data from databases for use in other programs, like taking your data out of Antelope and reformatting it for, in this example, HypoDD. You can also use it to put data back into an Antelope database. So we'll look at examples doing both things. It's good for combining and extracting information from multiple text files. All right, so if you ever have pieces of information in 4 different text files and you need to gather it all together and reformat it all into one file for one particular code, it's good for that sort of thing. And it does all the matching and searching and job control that you could do in a shell script. So awk. So I use Perl so that I never had to learn sed in some sense. Okay, so I can use Perl and it works like awk and it works like sed and it works like bash and it works like tc shell, and I could even run gmt commands out of it if I wanted to. So I'm going to start with a Perl example. So not a Perl Antelope example, but just a Perl example so that you can get a feel for the syntax. The first line looks much like any sort of shell script that you might write, except that instead of sh or csh, you are writing Perl. Now, if this doesn't look like what you're used to seeing, keep in mind I work pretty exclusively on Macs. Okay, so all of these examples are coming out of the Mac or the OS X operating system. The pound sign is used for comment lines. So here's just a comment header at the top of my file naming the script, which is phase2event.perl, and what it does. So this reads in like a hypodd sort of input file and extracts the origin information into an events catalog and extracts a secondary file called iddir.dat. So these 2 files are specific to a type of waveform cross-correlation package I use. All right, and then I write my name and the date. So now we're just moving on to how to read in files. Now here I have a usage line. So the @ sign indicates an array variable in Perl. So this says if the list of things coming from standard input isn't equal to 2, so if I don't write 2 things after the name of my command, then the whole thing dies and it plots to standard out a usage line. All right. And then if we move on, you see I'm just reading in the 2 inputs. Okay, so the $ indicates a scalar variable. I'm accessing the first element of my argv array, sending that to a variable called input, and then the second element of my argv array goes into Volcano. All right, now I'm going to open up that input file. So again, this is just to get you familiar with the syntax. So open to a file handle called in, the input file, or die, can't open input, and this $ bang just is going to give you the operating system error. All right, now I'm going to open my output files. Again, I just use the command open. My file handle for the events catalog is going to be EV, and the greater than sign indicates that I'm opening the file for both reading and writing. And again, if it can't open the file, say I don't have permission in the directory that I'm in, it's going to die, and I'm going to get the operating system error. And then the same thing for iddir.dat. Finally, in this file, what I'll do is I'll just go through each line of my input file, and that's what this while loop does. So while I'm in the file handle in for every line, that's just going to allow me to cycle through that file. All right, now I'm not going to show you the whole code. I'm just showing you the major syntax that I want you to keep in mind. And then since this is Perl, what we would do is exit this text file, go back to my Unix command line. I like to change the mode, or I like to make my Perl scripts executable, and then I just run them like here, right? So phase2event.perl, my Alaska Volcano Observatory phase file, and then which particular volcano earthquake, or which earthquakes at which volcano I'm interested in. All right. So the Antelope Perl interface is called Perl DB. You can find all of the commands that come with Perl DB on the BRTT webpage. I have the link here. You can also just Google Perl DB. If you already have Antelope installed, you can go back and find it in the documentation that is on your machine. All right. BRTT sends out a lot of example scripts for the Perl interface. So those are all found in your, wherever you have Antelope in an examples Perl directory. I'm not going to show any of those examples. They can get really complicated. So everything I'm showing today is actually, I think, a lot simpler than some of these examples that you can find in example Perl. Now, let's say you want to access the interface. You do have to change how you start your script. So this block of code is what I use to essentially turn on the Perl that comes with Antelope and the Perl interface, the Perl Antelope interface. All right, so this is the very first line of your text file. Then I have an eval command here, if 0, and then I open up the Antelope Perl library and then say use data scope. So if you remember, if you have experience with Antelope or you remember back to my original webinar, data scope was the kind of the seed database that was Antelope before Antelope existed. All right, so let's look at an example. This one is called Database 2 HDD. You'll see a theme here related to my own research interests. This takes information out of an Antelope database and outputs it into HypoDD, PH2DT, or TomoDD format. Right? So I do a lot of relative earthquake location. Again, since I want to use the Antelope Perl interface, I start with that block of code, and then of course I write my own comment lines telling someone who's reading this what this code is going to do. Now it's going to read in the arrivals table and origin table and a bunch of other tables just to essentially get arrival time information and initial earthquake locations out. This particular code takes 5 inputs. You have to give it the database, your output file name, a start date, an end date, and a minimum number of arrivals. Okay, so again, we're just going to cycle through that argv array and set up a bunch of variables, including the database name, the output file, the start date, the end date, and the minimum number of arrivals. So we could also replace this whole argv with just the word shift, and it would automatically shift through the argv array. All right, now we're going to open up our output files. The way this particular code works, you open up a temporary file that gets named after the database, and then it's .hdd, and then you have your final output file. So both this temporary file and the output file get opened for writing. Now, we're just going to start accessing our Antelope database. So to access the input database, we would use a command called dbopen. All right, so you're not going to be able to use dbopen unless you have turned on the Antelope Perl library. So you're going to notice a lot of syntax and naming convention that goes along with this. So dbopen opens up a database, right? You give it the database name, you read in the, or you open the database for reading in this case. I don't write to the database in this particular code. You look up a specific table, like the arrival table. Then you join that database with another table, the assoc table. So db lookup is used to look up tables, and then you have a lot of the same functionality that you would have on the command line, the Unix command line with Antelope. So db join, db sort, db subset, things of that nature. So for this particular code, I need the arrival table, the assoc table, the origin table, and the origin error table. Then I'm going to sort using db subset and again, this specific format. So I have this array pointer to my database, and I just keep adding to it and modifying it as I go along. So sort by number of or subset by number of associations, sort by time, station, and phase type, and subset again using my start date and the end date that I provided when I ran the Perl script in the first place. All right, now I need to cycle through my database, or my collection of tables. So I can use dbQuery to figure out how many records exist after all of that sorting and subsetting, and I just throw that into a scalar variable called inRecords, and then I have a for loop that's going to loop over all of the records left in my database after I've sorted and subset and added everything together. All right, so for record count in these for loops that you need to cycle through your database, it's always the third element of the DB that you're cycling over. So the third element of DB, again, through to in records, plus, right? And do it by 1. As I do that, line by line, I'm going to actually get information out of my database. So I'm going to use the command dbget and then give it my database pointer, and then get out evid, station, phase, time, del time, and delta. All right, and then send it all into variables named the same way in Perl. Now what I do with it is I just print it out into my temporary file. I do this for all of my temp files. I do this for all of the records. I have this temp file, I close the temp file, I reopen it, and then I do a whole bunch of other stuff that I'm not going to show here. All right, but just keep in mind the syntax, dbQuery, dbgetv. You're going to see the same sort of syntax pop up in MATLAB. What's only going to change is what this looks like back through here. All right, so that was getting information out of an Antelope table. Now we're going to look at an example that gets information into an Antelope table. This one is called Web PDE to Origin. Now this is what you would download from the PDE catalog from the internet 2 years or more ago. All right, so this won't work with what you can get now, but it used to work. We have a usage line. We go through our 2 input files, including the database name. We open up the database. This time we open up the database for reading and writing, so R+. We look up the origin table. That's what we're going to work with, is the origin table. Then we open up our list of earthquakes, and as we go line by line through our list of earthquakes, we're going to gather up some information. We're going to turn our time in particular into epoch time. So notice I make a string here that is a regular kind of readable time, and then I use string to epoch to switch over to epoch time, so that this time variable is now in seconds since 1970. And then I use an Antelope Perl command called dbaddv. I specify that I'm working with that origin table, and then I just add my information. Now the big benefit here is that all these Antelope tables are fixed formats. So I could do the same thing with printf, but by using dbaddv, I really have a very simple syntax here: time, and then my variable, latitude, and then my variable, longitude, and then my variable. And I no longer am worried about accidentally having my %10.2 in the wrong place and breaking my tables. All right, so this one down here closes the while loop. All right, so those are 2 really simple, 2 pretty simple examples. If you're interested in the full scripts, just email me. What do I tend to use this whole thing for, other than reformatting? Another use I've had is integrating the US Array National Facility catalog with flex array data. All right, so the TA and various flex array experiments have passed through the footprint of the cooperative New Madrid seismic zone, or seismic network. So it would be silly for us not to combine both the IRIS US array data with any available station information we can get. All right, so in order to address our research goals for our flex array experiment Nelly, we need to combine everything we can get from 2011 through to the present. And I've done this using a combination of Antelope and Perl, the cooperative New Madrid seismic networks. It's a network operation, uses earthworm, web services, shell scripts, and cron jobs to run this kind of all overnight, so we can kind of get everything all together in one Antelope database. All right, now let's switch over to MATLAB. The Antelope toolbox for MATLAB has existed for quite a long time. It was originally contributed software provided by Kent Lindquist, so we all owe him a round of applause or a beer next time you see him. There is a PDF available called the Antelope Toolbox for MATLAB. This is the most definitive source of information, and you should go find that. I have it off of one of my websites, but I'm sure with Google you could find it even faster. What the toolbox does is allows you to take advantage of Antelope's ability to read multiple file formats and get those multiple file formats into MATLAB. All right, and then once everything's in MATLAB, you can do whatever you want in MATLAB. So you have the full flexibility of MATLAB at your fingertips, right? So you can design your own processing stream. Now, Kent Lindquist emailed me a couple of days ago and gave me permission to tell you all that the MATLAB interface will become standard with the 5.4 version of Antelope, which is going to be coming out in May 2014. So I know I can't hear your applause. Everyone is very excited. I'm sure that we will no longer have to install it ourselves. But until May, for now, you still need to install the interface. All right, so the interface is available on GitHub under the Antelope users group. And when I install this on my machines, I use local make for the install, and there's a wiki also on GitHub that goes over how to compile the MATLAB interface for your own machines using local make. But we won't. Okay, so let's say you have the MATLAB interface compiled and installed, and your Antelope is speaking nicely to your MATLAB version. I haven't had any major problems on my Macs. I'm running Antelope 5.3 with MATLAB 2013A on 64-bit machines. So that's been pretty stable for me. So now we're going to be in MATLAB. All right, so we're in MATLAB. The first thing you need to do is set up Antelope. So here I'm setting an environment variable in MATLAB, right, called Antelope, and then it just points to my Antelope install directory. And then I'm going to run the setup antelope.m file that comes with the package. All right, so you can do this however you want. You can set this up as a job that runs every time you open up MATLAB. You can do it every time you open up MATLAB, whatever is most convenient for you. Now I'm actually going to work directly through an example out of Kent's MATLAB toolbox PDF file. All right, so we're going to work with an example database called the demo database, and to load that up, we're just going to run this interface command called dbexample get demo db path. All right, so the output of that is simply a MATLAB variable called demo.db path that points to the path to this demo database. Now, if we did that on the command line and used DBE or the DB editor to look at the demo database, that's what I'm showing up here at the top. All right. Now we need to open our database. So all we're going to do is say db equals db open, the path to the database, and we're going to open it for reading only. So notice that this looks really similar to the Perl interface. All right. So in some sense, once you have gone through the learning curve of one of the interfaces, all the other interfaces, or some of the other interfaces at least, become much easier to learn because you already are kind of familiar with the syntax of how they all work. All right. Now, in MATLAB, this DB is actually a structure. Okay, so here you can see it has database, table, field, and record. It's called the database pointer. So you don't actually see anything that looks like the DB editor output up here, but we've opened it up, and now just like in Perl, we need to load in a bunch of tables. So in this case, we're going to look up the origin table, and we're going to add it into the same database pointer. All right, so when we do that, table goes from being -501 to say 19. All right, so that 19 is just the table number. All right, so the origin table in this particular schema in the interface would be called table 19. So that just means it actually worked. Okay. Again, let's query how many origin records there are. We can use db query inside MATLAB. So we say db query, we specify our database pointer, and then the field that we're interested in this case, db record count. All right, we send that to a MATLAB variable inrex, and for that demo example, we would get 1351, okay, which is the equivalent to the last used ORID value, because this is a very nice database. Now let's say we wanted to actually just get out a list of all of the ORIDs in the database. So we again use db-getv just like in Perl. So db-getv, the database pointer, and in this case we're interested in all the ORIDs. So we just specify field ORID, and now we have a vector ORIDs which contains all of those origin IDs. So then we can do regular MATLAB things to it. I just, I could have done mean, but I did range. So what's the range of all of the ORIDs in the new MATLAB ORID vector? And the answer is 1350. Mostly because in this demo database, the earthquakes start at 1 and there's 1300 and go to 1351. All right, so that was an example for accessing one field. We frequently want more than one field out of a given table. So how do you do that? This is an example of that where we have latitude, longitude, depth, and time that we're getting out of that origin table, and we're just sending them to latitude, longitude, depth, and time in MATLAB. All right, and then I've just plotted them up. Now, yes, you can laugh. How can she make such ugly figures? We don't actually have the mapping toolbox installed on the MATLAB in my lab, so I can't picture Japan, but in your mind, think of that as Japan over there. All right. So once it's in, you can do whatever you would want to do regularly in MATLAB. The time is handled much like in Perl, so there's epoch to string and string to epoch available in MATLAB. There's this one, string year day time, which just takes epoch seconds and makes it nice and readable and would output it as like that on your MATLAB command line. All right, so a standard readable format. All right, so that's accessing the fields in the various tables, but how do you get the waveforms in? There's a couple of ways that I'm going to go over. One is called traceload_CSS. So obviously it assumes that you're dealing with a CSS database. this is in many ways the best way to go about doing it. So it's a two-step process. First, you use trload underscore CSS, specify the database pointer, and then the time and end time. So in this particular example, the start time and the end time that I'm interested in would have been defined on another MATLAB line above. All right. Now notice that trload CSS, I'm sending it to something called tr. This tr is a MATLAB structure, much like db was a MATLAB structure, but this one is called the trace pointer. All right, so you wouldn't send the output of trload to db, right? There's a reason this does not say db. So you use trload CSS, you specify the database, the start time and the end time, and then you want to send it to the trace pointer. And then once you have that trace pointer, you use trextract underscore data to get the data, to get data vectors out. Okay. There's also this command trgetwf, which also can get some data out. I'm not going to spend too much time. We're going to look at an example using trload underscore CSS instead. All right, so if we're in DBE, in regular Antelope, and we got everything, we sorted our tables, and we got it to the point where we just had one channel and one station name for a particular time period in our WOOF disk, we could say, view waveform or under the graphics command, and we would get something that looks like this. So we're going to recreate this in MATLAB using the data interface. All right, so what we're going to do is first we need the WOOF disk table. Now notice there's a P wave on this example, so we also need the arrival table. So we're going to look up the WOOF disk table, we're going to look up the arrival table, and then we're going to join them together. All right, so DB and DBT were two separate database pointers, and then we're going to join them into the DB database. Then we're going to subset. So subset where the arrival channel is equal to the WOOF disk channel. All right. Then we're going to load in the assoc table, join that to our pre-existing database, look up the origin table, and join that to our pre-existing database. So if we did all of that and then we looked at the records and arranged them so that they made sense, they would look, we'd have something like this, all right, where we had a station, a channel, a time, and end time, and we subset them. We'd have a station, a channel, a time, and end time, right? And we'd have one record. So here is an example of using DB subset in MATLAB, where we said the database pointer and then again, just kind of a standard format, right? Station equals CHM and channel equals BHC. Now our database pointer really only contains this one record. All right, so just like I'm showing here out of the DBE view, this MATLAB database pointer only contains one record. We can use dbgetv and point to it to get the start time and the end time of the actual waveform in this record. All right, and then we're going to use that start time and end time combined with trload underscore CSS to set up our trace pointer. All right. Once we have our trace pointer set up, we can use trextract data to get the data out. So now data 1 is a vector of amplitudes. All right. So we can get to plotting. But first, since I want to have the P wave on my waveform, we need to get some other things out of our database. So I'm going to use dbgetv to access our database, DB, and get out the phase and the arrival time information. And then I'm going to use dbgetv on our trace pointer to get out the number of samples, the sample rate, and again, the begin time and the end time. All right. Now I do that so that I can do all this plotting down here, right? And after we go through all that, which that's all MATLAB, I'm not going to go over that, we would get something that looks like this. All right. So nice black and white image instead of the blue and yellow that we grow used to when using Antelope. Okay, some pointers or tips about pointers, as the case may be. It's really important that you remember that the DB and TR, which is what I called them in this example, or that database pointer and that trace pointer, don't get cleared, the memory associated with them doesn't get cleared by using the MATLAB clear command. All right, so there's two commands that come with the MATLAB Antelope interface. One's called db close and one's called tr destroy. And if you run into problems when you're doing your first few Antelope MATLAB interface programs where your MATLAB slows down considerably or you're running into memory issues, it may well be it's because you didn't properly clear the memory or close your database when you were done. All right, so please do not forget that db close and tr destroy exist because you will need to use them. All right, so the MATLAB interface comes with commands that allow you to evaluate response, access Antelope parameter files, etc. Again, Kent Liquid's MATLAB toolbox document has a lot of detail. Here I just have the commands that would be used in relation to response. So db response and eval response, and just like you have to free the memory associated with the database pointer and the trace pointer, there's a command that allows you to free the memory for the response information. This is a MATLAB function that would read in a database, a channel, a station, and a vector of frequencies, and go get the response information out of the database to move towards removing it, okay, from your waveform. So this is all just looking up all the tables you need that contain information relevant to response, and then you would say db response, you'd get the name of the response file out, and then you'd use db response to build the response object, and then you would evaluate that response object at a particular set of frequencies that you're interested in. All right, so what have I been using the MATLAB Antelope interface for? One thing is to create noise, power spectral density, probability density function plots for restricted data. So if your data is sitting at the DMC and it's not restricted, you can request these PSD PDFs directly from Iris, and they'll send them to you. And they come in this .bin form, and there's a nice MATLAB command to view them, and you'd get something that looks like that, power versus period, with this probability density function, and you could assess whether or not your station is quiet, like high noise model or low noise model. So this all follows McNamara and Bose's method. Now, if you have restricted data, however, Iris won't send you these .bin files, so we've been working on a recreation of the McNamara and Bose method in MATLAB. Okay, so that's all still in progress, but all of our data resides in an Antelope database, so obviously we're querying the Antelope database and then sending it through subroutines that recreate these PSD PDFs. All right, another thing, we had an array of 19 stations sitting out above the New Madrid seismic zone. This was an Iris Pascal experiment. Shout out to Bob Smalley for taking this beautiful picture. This is the Mississippi River up here. What we were interested in doing was broadband FK analysis to look at various signals coming across the array. This is just an example of the BBFK analysis for the P wave for a local earthquake. We ended up Blaine Buckholt was working on this, wrote most of these codes. We end up sending our waveforms out of Antelope and into MATLAB and go do the BBFK analysis and removing overlapping windows. All right, So it takes a long time. Lane was very patient. So another example, this is more of what I would work with more directly myself, is cross-correlation. This is cross-correlation using the Gizmo package. And then ultimately, I'm interested in improved differential times for, again, earthquake relocation and tomography approaches. So this just uses Gizmo's Antelope Matlab interface to do cross-correlation. It's a really nice package. There's the waveforms before cross-correlation, there's the cross-correlation coefficients, and then there's the waveforms realigned after cross-correlation. And this particular example comes from onshore-offshore data. And the reason I picked that is because you can't tell, but the database contains land data that's stored in Miniseed and offshore data that's stored as SAC files. All right, so using the Antelope interface, everything is seamless. You don't have to worry about which data is in which format. Right? So I'm going to finish up here. Just to learn more, always remember this is Antelope is a BRTT product. You can go to their FAQ page. A lot of times Antelope is used for data archiving, so I have Pascal's data archiving information up. Antelope user groups have workshops all around the world, and slideshows from those workshops can be found down under the BRTT main page, and then you can find some information from Pascal on previous workshops talking about Antelope and Matlab and Python, which never send me a Python question, just putting that out there. You can find that on the Pascal webpage. All right, so thank you all for listening. I know I went quite fast, and I do want to thank Kent Lindquist for writing the MATLAB interface, Frank Vernon for making me learn Perl my first semester in graduate school, Celeste Reyes and Mike West for the Gizmo package, which I really have been enjoying using, and then of course BRTT and Iris. And the next Antelope user group meeting will be in Azerbaijan, all right, in May. So I guess if you're sitting on a pile of money, you can go to that. Thank you.
Awesome. Well, thank you very much, Heather. That was great. Earlier in the talk when you mentioned the MATLAB integration in 5.4, you alluded to clapping, and there were some e-claps that came in from Bill Harbert and Glenn Thompson. They both made some very excited comments about that. So that's a great extension that's happening for that. So I would encourage anybody, if you have any questions, write them in. You can write them in now. I just had a comment come in from Tim Bartholomew's that said that was a great introduction. Thanks a lot. And there were only the 2 comments to start out. So if there are any questions, hopefully they get submitted now. And I just had a sort of a background question for you, Heather. How long have you been using Antelope?
I've been using Antelope since 1999 when I started graduate school.
Awesome.
So I think that makes me an early-ish adopter, but yeah, Frank Vernon suggested that we use that with our original Costa Rica data set back in 1999.
Great. All right, there's a comment from Glenn. Glenn asks, or says, starts out, Gizmo is in principle a set of MATLAB classes and packages for importing, exporting, processing, and plotting seismic data in a variety of formats. We also added catalog, event, and event rate classes. These need further work, but the idea is to add importers and exporters for common earthquake catalog formats and build a useful set of routines for plotting these kinds of objects. So I think that was more of an FYI.
Okay. Yeah, actually, we've been using the waveform suite and Iris web services tools to do teleseismic cross-correlation using the GSN stations, but no Antelope involved in that, so I didn't
Excellent.
focus on that in my talk.
I have a question from Alberto Lopez, and his it's a sort of a two-parter. He asks, "Have you used DB to pH and DB correlate, and how do they compare to the other functions that you described here?"
So I have not used DB correlate. And I'm going to imagine DB to phase does very similar sorts of things to what I described, except, I just carry around what I wrote back in the early aughts. So I don't think DB to pH would have existed back when I wrote some of my codes, and so I still just use what I wrote.
Okay. Well, if there's no other questions, Heather, are you available for if people wanted to email you questions? Would you be available for answering those? Is that
Yeah, sure, sure.
okay? Okay, there's one more that came in. This is from Amir El Sharkway. I have a question about the spline and what is the B spline in MATLAB?
I am not entirely sure I am the person you should be asking. um, if maybe offline, if they want to email me a specific example of how they're using it and why it's not working or something, I can help. But
Okay. All right. Well, if there's no other questions out there, you can direct them to Heather later. And yeah, Heather, thanks again. I really appreciate you coming back to give a sequel talk. The original Antelope uh, webinar was, I think, has 1,280 views now. So it's clearly been really useful to folks, and
wow,
I think this will be as well. So thanks for taking the time out to do this.
you're welcome.
Yeah. All right. Well, thanks everybody for coming, and we'll see you at the next webinar in 13 days. So thanks again, Heather. Take care, everybody.